Have you ever wondered what separates software that just feels right from the apps that are clunky and unreliable? Well, I can tell you, it's not magic. It is 100% intentional design. Today, we're going to crack open the architect's playbook and see exactly how great software gets built on purpose.
So let's start with the big question, right? What's the real difference between good software and great software? Good software, it works. It does the job. But great software is reliable. It's snappy, and you can keep adding to it over time without the whole thing falling apart. And that difference, it absolutely does not happen by accident. It's all about specific, deliberate choices made way before anyone writes a single line of code.
All right, here's our game plan for this explainer. First, we'll look at the framework architects use to even define what quality means in a way you can measure. Then, we're going to open up their toolkit and talk about something called tactics. From there, we'll do a deep dive into 3 of the big ones that you, as a user, feel every single day: availability, modifiability, and performance. And finally, we'll wrap it all up with the key takeaway: the sheer power of deliberate design.
Look, if you want to build something good, you have to agree on what good actually means. You can't just tell an engineer, hey, make this thing fast and reliable. That's way too vague. Architects need a super precise, measurable way to talk about these qualities.
And this is how they do it. This thing is called a quality attribute scenario, and it's basically a shared language for quality. Let's break it down. There's a source. That's who or what causes something to happen. It generates a stimulus. Think of 1,000 users all trying to log in at once. That stimulus hits an artifact in the system, like the authentication service. All of this happens in a certain environment, like, say, under normal operations. The system then has a response, and this is the most important part, a response measure, a specific number that tells us if that response was good enough.
So that's the theory, but here's where it gets real. Let's apply this to availability, just keeping the lights on. The stimulus could be a fault, like a server crashing. The artifact that's affected is that server. The response we want is to detect that crash and recover from it. And the response measure? Now we're talking specifics. The time to repair must be under 5 minutes. All of a sudden, a fuzzy goal like be reliable becomes a rock-solid engineering requirement you can actually build and test against. Okay, that's cool. We can now define our quality goals with pinpoint accuracy. But how do we actually hit those goals? Well, for that, we need to open up the architect's toolkit and introduce the idea of tactics.
So what is a tactic? It's really simple. It's a design decision. It's a specific, concrete move an architect makes that directly shapes how the system is going to respond to something. It's not a wish or a hope. It's an actual architectural technique used to control for a quality attribute. This diagram really says it all. You've got a stimulus coming in on one side, a server failure, a flood of user requests, whatever. And on the other side, you have the desired response you need to achieve. Tactics are that bridge in the middle. They are the control knobs, the levers, that the architect designs into the system to make sure you get from the stimulus to the right response. They are the how behind the quality.
All right, let's make this super real with our first deep dive. We're going to start with maybe the most fundamental quality of all: availability. This is all about making sure the system is actually there for you when you go to use it.
I mean, we've all been there, right? Staring at that spinning wheel of death or a service unavailable page. It's frustrating. At its heart, availability is just this. The software is online and ready to do its job when you ask. The architect's mission is to design a system that can handle faults so that any outage is kept within acceptable limits.
And here is a perfect real-world availability scenario. The source of the event is a heartbeat monitor. It's like a little process whose only job is to constantly poke the other parts of the system and ask, "You alive? You good?" The stimulus is when one of those servers suddenly goes quiet. The response we want is to immediately tell a human operator. And the response measure, the big goal, 0 downtime for the end user. That's proactive fault detection in action.
Now let's tie that heartbeat example back to our general framework. See, that unresponsive server is what we'd call a crash or an omission fault under the stimulus category. The system's reaction, notify appropriate entities, is a textbook response, and our goal of no downtime, that slots right into the response measure bucket, along with things like time to repair. You can see how the specific story maps perfectly onto this general model.
So, what's in the toolkit to make this happen? Well, for availability, it's kind of like a 3-pronged attack. First, you have to detect faults, using tactics like ping/echo or that heartbeat we just talked about. Once you know something's broken, you have to recover from it, using things like active redundancy, which is basically having a hot spare ready to go, or rollback. And of course, the best of all is to try and prevent faults from ever happening in the first place.
Awesome. So our system is reliable. But, no software is ever really done. It has to evolve. And that brings us to our next deep dive, modifiability. This is all about designing for change.
In software, change is the only thing you can count on. You're always adding new features, squashing bugs, adapting to new tech. Modifiability is all about making sure the cost and the headache of making those changes stays under control. A system that's easy to modify can live a long and happy life. One that's a nightmare to touch, well, it's probably going to stagnate and die.
Here we go, a classic modifiability scenario. The source is a developer. The stimulus is a request to change something in the user interface. The response is actually making and testing that change. And check out that beautiful, crystal clear response measure. Get it all done in 3 hours. That's a modifiability requirement.
And if we look at the general scenario, you'll see the response measure is all about cost. It can be measured in effort, person-hours, or in calendar time, like our 3-hour example. It could also be the number of components you had to touch. No matter how you slice it, a highly modifiable system is one that keeps these costs low.
So what's the toolkit for this? The main goal is to tame complexity. You see tactics here like reduce coupling. Think of that as preventing different parts of the system from being tangled together like a mess of spaghetti. Then there's increase cohesion, which is about keeping related code together in one place. When a system's well organized like this, a change in one spot doesn't cause a chain reaction of problems everywhere else.
Okay, our system is reliable and it's easy to change. But there is one more thing users care about, a lot. Is it fast? Let's jump into our final deep dive, performance.
Performance scenarios are all around us. In this example, users are starting transactions. The system has to process them. And the response measure is perfectly clear, an average latency of 2 seconds. Not fast, not quick, a specific, measurable number that we have to hit.
And this really gets to the core of it. Performance isn't just a feeling. For an architect, it's about one thing, time. It's about the system's ability to consistently meet its timing requirements.
So how do architects make sure they hit those performance targets? Their toolkit is all about balancing demand and resources. It's a two-sided coin. On one side, you have tactics to control resource demand, stuff like prioritizing critical requests or making the system more efficient. On the other side, you have tactics to manage resources, things like adding more servers, using concurrency to do more at once, or being smarter about scheduling tasks.
Whew. Okay, we've looked at the framework for quality, and we've peeked inside the architect's toolkits for availability, modifiability, and performance. So what's the one big idea that ties all of this together?
It's this, right here. Quality is not an accident. It never is. The best software, the most reliable, the fastest, the most flexible, it doesn't just spring into existence. It is the direct result of architects making conscious, deliberate design choices, using specific tactics to hit clearly defined and measurable goals.
So I'll leave you with a final thought, a little challenge. The next time your favorite app gets a seamless update with some great new feature, are you just going to see an update? Or are you going to see a successful modifiability tactic at work, something that was probably planned years in advance by a really thoughtful architect? Thanks for watching.